Now we'll continue on going through page 2 of the notes and look at how do we work with determining a vector given 2 points. So I started with my example on the top of page 2. I have the initial point of the vector v. I want to be the point -3, -5. Notice the parenthesis notation, that is a point, that is not a vector. And I want the terminal point to be the point 1, 4. So the tail of the vector will begin here. The head of the vector, or the end of the vector, will be at this point. I initially drew in my 2 points. So I have the point -3, -5, and I have the point 1, 4. Draw the vector with the tail to the head of the vector. Now the length of this vector is the magnitude of the vector, and the angle that this makes with either a horizontal line or possibly a vertical line, depending on how we want the direction being listed, is going to be something we're going to have to locate to get the direction. Now the rule, if I just learn a rule for determining what the rectangular or component form is of the vector, if I have it give the points given to me, is to take head minus tail. So I can take, like a machine, take the head x-coordinate minus the tail x-coordinate, as shown here, and take the head y-coordinate minus the tail y-coordinate, as we show here, and do the little simplification, and I'll determine what the vector is that is from this initial point to that terminal point in a rectangular form or component form vector. However, if you look at the picture, notice that I would have to go, to get from this point to this point, I would have to go over 4, and I could count up 9. So this vector definitely makes sense. Always draw a little sketch and make sure that your vector notation makes sense in the end. I do need the pointy parentheses here, or the arrowheads at the end, because this is now a vector. Now this vector 4, 9 does not actually have to start at the point -3, -5. I could have started it in standard position and placed this little tail down at 0, 0, and then the head of the vector would have to be up located over 4 and up 9. To determine the length of the vector, good old Pythagorean theorem, so it's very close to a length of 10. And then if I want to find the angle that my vector makes with the positive x-axis, it is actually nice to either move this vector to standard position and have it as the little tail here and then over 4 and up 9, or I can draw a line that is parallel to the positive x-axis and think this angle and this angle would have to be the same. They would be corresponding angles. And so if I think of what type of a picture, if I do have this setup where I go over 4 and up 9, that my opposite side would be 9 units long and my adjacent side would be 4 units long. So the tangent of my angle would be 9/4, and a good old inverse tan function will give me that 66 degrees. Now if I asked what angle does the vector make with the positive y-axis, then I would need the complement of the angle that I had already found, and that would be 24 degrees. This is the type of angle that you'd want to end up using if we were dealing with the bearing of this vector. The bearing of the vector is referenced from north, so if I moved or think of the northbound line that would come through and be a component of this vector, and I would need to move clockwise 24 degrees to get to this vector. So this vector has a magnitude of square root of 97, and it would have a bearing of 24 degrees from north. So a generalization is anytime you're trying to find the magnitude of a vector, and if I know that this is my initial point and this is going to be my terminal point of my vector, the picture of the vector would look like this. And Pythagorean theorem would tell us that you can always find the magnitude of the vector by finding leg squared plus leg squared and square root to find the measurement of this hypotenuse. So Pythagorean theorem will always be used for magnitude. And as we talked about on the previous page, the absolute value is what notation we use to describe the magnitude of the vector, its length. Now, we talked about on the first page and at the top of this exercise that rectangular or component form is one way to describe a vector. We actually have some other forms that are similar. These two are similar to each other, which could be called a common form or a polar form. This is probably the most common notation, is to call it a polar form vector. And it's where we deal with the magnitude listed as the first component of the vector and its direction as the second component of the vector. So our standard position or our standard form of having the rectangular or component form had this number be the x movement, so the horizontal movement, and this number be the y movement. Now in common form and polar form we have something different happening. If this is my vector, then I have a magnitude or a length as the first component, and then I have a direction that can either be written as a bearing or as a standard position angle. So these two vectors, whether I have it in the common form or in the polar form, they are not going to look the same unless this angle happens to be a 45-degree angle here. For instance, if I had this vector and I tell you that I have 14 miles and I have an angle here of 60 degrees. There's the magnitude or the length of my vector, and here is an angle for my vector, but I would need to describe to you what this angle is standing for. Is it a standard position angle, or is it a bearing? If it's a standard position angle, then we would say go up 60 degrees, that's a standard position, and the length of this vector would need to be 14 miles. And so this would be considered a polar form vector if I give you the angle in standard position. Now on the other hand, if I said no, this is a bearing, they would be different vectors. If this were given as 14 miles, and I tell you that the 60 degrees is a bearing, that means that's the measurement from north, and that means I would need to go 60 degrees from north in the clockwise direction, and this angle would be 60 degrees, and the length of this vector would still be 14 miles. We call this form in this class the common form vector. I can spell. If I have this angle in standard position, we'll call that the polar form. So polar form vector is reference that the direction angle is from the positive x-axis rotating counterclockwise, as opposed to the common form vector will be a bearing measurement for the direction, and we'll have the angle referenced from north but going clockwise. And that's it for page 2.